Hello everyone, welcome to the 11th episode of the series. In this video, we'll talk about determinant and its properties. So we have already seen the determinant of a 2 by 2 matrix in one of the earlier episodes. And for a matrix given by entries A, B, C, and D, the determinant is given by AD minus BC. We also saw a formula for the inverse of a 2 by 2 matrix in terms of the entries of the matrix A and the determinant. The goal of this episode and the next few episodes is to generalize the idea of determinants to all square matrices. So let's talk about the idea. So for any square matrix A, we can define a number determinant of A, which satisfies two fundamental properties. The first is that A is invertible if and only if the determinant of A is not equal to 0. And the other is that the determinant distributes over a product of matrices. So determinant of A times B is the same as determinant of A times the determinant of B. So note that property 1 implies the following four properties. The first is that if the inverse of A exists, then the determinant of A is a non-zero number. If the determinant is a non-zero number, then the inverse exists. If the matrix has no inverse, then the determinant has to be 0. And if the determinant is 0, then the matrix cannot have an inverse. Okay, so let's look at an exercise. So we're given two 2 by 2 matrices A and B, and we want to verify that the determinant of A times B is the same as the product of the individual determinants. So first, we're going to compute the determinant of the product of product AB, and you can multiply these two matrices and verify that it's indeed 1, 8, 3, 4. And its determinant is going to be 1 times 4 minus 3 times 8, and that's minus 4 minus 20. And next, we can compute the determinants of A and B. So the determinant of A would be 3 times 2 minus 1 times 2, that's 4. And minus 1 minus 4, that's minus 5. And 4 times minus 5 is minus 20. Okay. When we write the determinant of an explicit matrix, we just replace the brackets with vertical lines. For example, if you're given a 2 by 2 matrix 3, 2, 1, 2, and we want to write its determinant, the shorthand notation would be just writing our entries of the matrix between two long vertical lines. And one more thing here, this symbol with a colon and equality sign defines the left side to be equal to the right hand side. So this is the symbol for definition that mathematicians usually use. We're first going to explore the properties of the determinant and then use them to compute the determinant of A. We're also going to add a third property to the list of two properties that we saw earlier, and this property being that the determinant of an identity matrix is 1. Now, these three properties completely determine the determinant and all of its properties. Let's look at another exercise. This is an important one. So we want to show that if M is invertible, then the determinant of its inverse is the multiplicative inverse of the determinant. So we're going to start with the fact that the determinant of the identity matrix is 1. And because we can write the identity matrix as M times M inverse, we can replace the determinant of identity by determinant of M times M inverse, and by the distributivity of the determinant over product of matrices, we can write it as determinant of M times the determinant of M inverse, and then we can just divide by the determinant of M on both sides, and we get the identity as required. So for example, if the determinant of M is 7, then M is invertible and its determinant is 1 over 7. So determinants also play nicely with row operations. So swapping two rows multiplies the determinant by -1. Multiplying a row by C multiplies the determinant by C. And adding a multiple of one row to another row does not change the determinant. So here are some examples of elementary row operations and their effect on determinants. So the first example, we see two rows being swapped, and as it would turn out that the determinants on the left and the right hand side differ by a factor of -1. In the second example, we've pulled out a factor of 4 from the second row, and as it would turn out, that the determinants differ by a multiplicative factor of 4. And in the third example, um, we've added -4 times row 1 to row 2. And if you compute the determinants, you will see that the determinants are the same. So adding a multiple of one row to another does not change the determinant. So there's one more property that I want to talk about, and that's the relationship between the determinant and the transpose of a matrix. So it turns out that the determinant of a matrix A is the same as the determinant of its transpose. For example, if we have this 3 by 3 matrix and its transpose matrix on the right, the determinants are going to be the same by the property above. So this identity is remarkably useful because it allows us to deduce new determinant identities from old ones. So similar to the idea of row operations, we have the idea of column operations, and we can use the relationship between the transpose and the determinant to deduce that column operations also change the determinant in simple ways. So for example, if I have a matrix here, I can take its transpose. That's not going to change the determinant, and then I can do row operations on this transpose matrix, and we know how the determinant changes under row operations, and then we can take the transpose back. So effectively, using the relationship between determinants and transpose, we can learn what effect column operations have on the determinant. And with this, I would like to end this episode. I will see you guys soon. Until then, happy learning.